Hi everyone, welcome back to another episode on Feed Your Brain. Today we're going to be talking about general and special relativity, two of the most influential theories in the field of physics. So let's dive right into it. General and special relativity are two theories that were created by Albert Einstein, a physicist from the 1800s and 1900s. These two theories, general and special relativity, are part of a larger theory known as the theory of relativity. The theory of relativity has changed the course of physics itself. Now, the theory of general relativity states that space, the three dimensions of space that is, and the one dimension of time are actually interconnected into a fabric known as space-time. Space-time is actually four-dimensional since 3 and 1 sums up to 4, but it is usually represented as a two-dimensional fabric. It is also what is known as a four-dimensional manifold. This means that from the surface, it looks four-dimensional. If you were to stand on a four-dimensional object and gaze off into the distance, you would see a four-dimensional, well, it would look like you were on a four-dimensional object. General relativity states that objects with mass can distort the matrix of spacetime. Let me explain a little further. So let's say we have an object that is particularly massive. First, say the Earth. The Earth is very, very massive. Now let's take a lesser massive object than the Earth. In this case, the Moon would be suitable for this. The Moon is less massive than the Earth. It's more massless than it. Abiding by the rules of general relativity, a lesser massive object, in this case the Moon, and a more massive object, in this case the Earth, will have a relation that is to do with gravity. This is the main focus of both general and special relativity, that is gravity. Now, a massive object, that is in this case the Earth, creates a distortion in the space-time continuum. A more massless object, like for say the Moon, creates a smaller distortion. Because the more massive object creates a smaller distortion, which is often represented as a depression in two-dimensional illustrations, this will make the less massive object orbit the more massive one. You can even try this yourself at home. Take a sheet and get a massive object, like for say a basketball. Take a less massive object, put it at the rim of the sheet, and the less massive object will start to go around the massive one. Now, the less massive object will eventually fall to the center, but this is because of friction. In space, there is no friction. So the less massive object, in this case the Moon, and the more massive object, in this case the Earth, are in tandem gravitationally. This area of the object, or really the depression or distortion that the object creates in space-time, is known as a gravitational field. Now, gravitational field is often represented as a depression in two-dimensional illustrations because, or even in three-dimensional models that have a two-dimensional fabric, because this works. But with four-dimensional objects, it is a little bit more complicated, and you're gonna have a lot more impossible shapes with that. Now, the distortion itself, the depression, if you will, that the massive object creates in the space-time continuum is known as a gravitational field. A gravitational field is dependent on the mass of the more massive object. The more massive that object, the larger its gravitational field. That's why Earth only has one moon. However, a more massive object, like for say Jupiter, has a ginormous gravitational field and thus has 79 moons. There is actually a method to calculate the force of a gravitational field. It is a formula similar to E = mc², which was also created by Albert Einstein himself. The formula to calculate a gravitational field is known as F = G, m1 times m2 divided by r. Let me explain. m1, the mass of the first object, usually the more massive one, and m2, the mass of the smaller object, multiplied, and the output of that multiplication divided by r, which is the distance between those two objects, will give you the force of the gravitational field. Now, g is a gravitational constant, and it took a while to find out what g is, but eventually we did find out what g actually is. So if you take the output that you got from the mass of one object, multiplied by the mass of another object, divided by r, and then you multiply that by g, or vice versa, like it's presented in the actual formula, that will equal the force of the gravitational field. Special relativity aims to prove that space and time are interconnected. One example that many people in the world use commonly to explain this is, well, let's just say that you're looking at a clock. You're looking at the ticking of the hand. Very simple enough. You're looking at it at a certain distance. You're looking at a clock, maybe on a clock tower even, from a certain distance. Now let's say that you start to back away from the clock tower. Nothing really changes, right? The light from the clock tower, or more specifically, the photons coming from the clock tower, will take a certain amount of time to reach your eyes. The further you get away from the light of the clock, and even the clock tower, the more time it will take for those photons of light to travel that distance. Albeit, it will be very fast, way faster than that, but it will still take time. You might be wondering, how exactly does this prove that space and time are interconnected? Well, we have one point over here, that is the clock tower, or even just the clock. So that's point A, let's just say. And then we have point B right over here, you, or at least your eyes. If there's a certain distance between point A and point B, or in this case the clock and your eyes, and there's a certain object that has to travel from the clock to your eyes. This is the light coming from the clock. Now, let's say that this distance changes. Well, now you have a new variable in this example. If the light has to go over a longer distance, then if the light maintains a constant speed, which it will maintain a speed of 299,792,458 meters per second squared all the time, it will take longer to travel that distance. It will take more time. If you shorten the distance, it will take a shorter time. You elongate the distance, longer time. Shorten the distance, shorter time. The only thing that can change this, the only way that this can take the same amount of time as this, is if that light were to be traveling at different speed, which could happen if there was types of fluids that could potentially slow down the speed of light, which there actually are. But normally, air isn't enough to slow down light. So this always works. This relation between space and time. General and special relativity pretty much work in all fields of science. However, there is one particular type of field where general and special relativity fail and are not compatible. And that field is quantum mechanics, or quantum physics. Now, special relativity is compatible just fine with quantum mechanics, or quantum physics rather. The results are pretty much quantum field theories. But general relativity is a little bit more tricky, because if you tried to make it compatible with quantum physics, a lot of the maths are going to break down. Why? Well, because of a rule, a little something known as the Heisenberg uncertainty principle. Let me explain a little further. The Heisenberg uncertainty principle states that in the realm of quantum physics and particle physics alike, there is absolutely no way to be certain of something. Now, if you try to take, for say, a photograph of a muon, with light, it's not going to work because the light will just pass over or under or to the sides of the muon or muon. Because of this, you cannot use light to photograph a muon or any elementary particle for that instance. Now, why is this? Because light itself is an elementary particle. Photons are elementary particles. And because you can't use elementary particles to observe elementary particles, you're just using more elementary particles. It's if I wanted to observe a bowl of cereal with a bowl of cereal. Sounds ludicrous, right? Same problem here. Because of that, you cannot make any direct observations with anything that has to do with elementary particles or anything at that level, even atoms. Models of atoms use something known as electron tunneling, and they use electron tunneling microscopes. These are special microscopes that can detect the electric charge of electrons, and yet they're not 100% accurate. Because of that, you can never be certain with anything in quantum physics. However, we can still make theories, and we have. Quantum field theory is one prime example, which has aimed to solve a lot of the problems of quantum mechanics and has successfully solved a lot of them. Now, this gigantic theory of theories, which is known as the standard model of particle physics, gravity is not to be found anywhere. Nothing. It is not even mentioned at all. So, scientists are still hard at work to try to find out if gravity even exists at this scale. Now, if Einstein's theory of general relativity is not to be taken into consideration, then there is a possible candidate for a theory of gravity in the quantum world, and that is simply known as quantum gravity. What quantum gravity states is that gravity is a force. In fact, it is a fundamental force, like electromagnetism and the strong interaction and the weak interaction, which are the three other fundamental forces, and that it has its own boson. In fact, this would be the fifth and final Gauge boson. Well, until we find the dark matter axion. The graviton would be massless, since gravity begins at the speed of light. And we also would know that it would have a spin of 2. Spin is the property of an elementary particle where it has many axes that confine to their points, and when the particle rotates, the axes return to their original configuration. If gravitons were to have a spin of 2, that means that it would take 2 turns or 2 rotations for the graviton to take in order for these axes to return to normal configuration. However, there is one problem with proving this theory, and that's that it also states that if the graviton exists, it is extremely weak. Why? Well, let's just look at the forces of the forces. Now, the strongest fundamental force and the strongest force in the universe is the strong interaction, or strong force. The strong interaction is about 100 times the force of electromagnetism, which, by the way, is what phones use to communicate with each other. 100 times that force is the force of the strong interaction. The weak interaction is about 100,000th the force of the strong interaction. Gravity would be very much weaker than that. Because gravity is so weak, it cannot be detected by any machine in the world if the graviton exists. No particle accelerator, no machine, nowhere could detect gravity as a result. So, if this theory was true, we would never know if it was. We just have to refine our machines, and if we do find a massless particle with a spin of 2, it will most likely be the graviton. But we have yet to find it. So, we've made other theories to explain gravity. One interesting one is known as string theory. String theory says that every elementary particle, it can be broken down even further to what is known as a fundamental string. Think of it like this. We have a string, a fundamental string, and it's just like the string of a guitar. When you play it, you get a different vibration, depending on how you play it. Similarly, if you were to tune this string, this fundamental string, you would get a different elementary particle. And that includes the graviton. This is a way to introduce gravity into the standard model, but it does have its problems. This theory needs what is known as open and closed strings. Open strings are attached to a universe. Closed strings can hop between universes. Yes, universes. The multiverse, the concept of the multiverse, needs to be correct in order for this to be possible. And although it is very much believed by many people, myself included, it is not yet confirmed. So that's one problem. Another problem is that even if we were to push that aside, the whole multiverse thing, it would still have another problem: dimensions. Right now, we know that there are only 4 dimensions in the universe. 3 of space, the first dimension, second dimension, and third dimension, and 1 of time, the fourth dimension, that would actually be. I don't know how to use my fingers anymore. Anyways, if this is the case, then this would not be compatible with string theory, because string theory says that there has to be at least 10 dimensions for it to work properly. So scientists have tried to model string theory and erase those 6 extra dimensions. And the result does not work. The mathematics break down pretty quickly. As a result, this is not possible. Because we haven't discovered 6 new dimensions, and we probably never will, we cannot yet confirm string theory. One final theory to talk about is one that also involves something similar to strings: loop quantum gravity. Now, in order to understand loop quantum gravity, we need to look back at space-time. Now, what loop quantum gravity achieves to do is that it wants to quantize the fabric of space-time. So it wants to make smallest possible units of space and smallest possible unit of time. And this can be done via a very clever method, and that is known as discrete mathematics. What discrete mathematics does is that it erases all of the problems that continuous mathematics has, which is infinities and infinite probabilities, and the Hyperwebster, the Barnard-Tarski paradox, which research it. It's very mind-boggling. But all of those problems are gone with discrete mathematics, because it is only to do with discrete numbers that have an end and nothing more. Yeah, sure, there are decimals and it's pretty much mathematics, except with infinities and other things that continuous mathematics has. If discrete mathematics were to be used to find out if space and time are quantized, well, we do have a result. Space and time are able to be quantized. The smallest units of space are known as the Planck length, Planck area, and Planck volume. The smallest unit of time is known as Planck time. Now, these quantized versions of space and time are interconnected, or better yet, they're in the form of loops. And these loops build the space-time continuum. This sort of network of loops that loop into each other is known as a spin network. This spin network builds the entirety of space-time. Because of this, we now have an answer, right? Well, there are some problems. You see, this is just too small to be able to prove with any of the machines we have, and is even harder to prove than quantum gravity, for instance. We're talking about the smallest possible units of physics before mathematics themselves break down. And because of this, it is near impossible to find out these distances. However, there is one idea that has been proposed and actually attempted before, and that is the speed of light. Let me explain a little bit. Loop quantum gravity states that longer wavelengths of light travel faster than shorter wavelengths of light. This means that the redder a photon is, the longer its wavelength, the faster it will go. And the shorter the wavelength, or the bluer it is, the more it will go slower. However, these measurements would be too small to calculate, too small to observe with our current technology. But there is one idea that is particularly clever to find out if loop quantum gravity is true. And that is through the death of stars themselves, supernovae. When a star exhausts its fuel, it can die in one or two ways. If it's a star like our sun and a little bit bigger and smaller, then it will just simply expand 250 times its size, more or less, and then shed its outer layers and shrink down to just its core. This will leave a white dwarf. However, if the star is considerably massive, then it will exhaust its fuel over a long period of time, and then it will collapse 25% the speed of light and explode into a supernova. And the energy produced by these supernovae is only rivaled by the Big Bang, by the creation of the universe itself. Sometimes these supernovae are so potent, so powerful, that they let out a beam of highly energized light, gamma radiation. And the beam, the outbursts of this radiation, is known as a gamma ray burst. Gamma ray bursts are highly focused beams of gamma radiation, the shortest wavelength on the electromagnetic spectrum. Because of this, they have a lot of energy, and they could be fatal to life on planets if they were to, point at one. If the gamma ray burst could be observed, then maybe, just maybe, there's a chance that we could find light traveling faster than other light. So scientists attempted to do this, and they observed a gamma ray burst from a particular star, and they observed very closely the light that it emitted. And they didn't find anything. But scientists are going to still keep trying to find out if gravity can be compatible, and general relativity itself can be compatible with quantum physics. And just then, we will have a little bit of a more complete picture on the theory of everything. Thanks a lot for watching this video. I'm sorry that I took a long time. The green screen was cluttered absolutely, and there was a lot of things happening. I went on a trip or two, but I just wanted to say that I'm happy to be back, and I'm gonna be doing a biology series, hopefully next video, or one of these videos coming up soon. If you liked the video, leave a like, and if you like the channel, then subscribe, and make sure to turn on those notifications so that you don't miss whenever I upload a new video. Trust me, turn on those notifications. Anyways, that will be it for this video. I'm Nick, and my goal is to feed your brain. When is this cup gonna, please tell me? When? This cup is not, it's still full, it still has water.